In section 2.3, we actually start to talk a little bit more about atomic theory, such as what the atom is made out of, but even more importantly, how do we know in the first place that there are things such as atoms in the universe, and that's what all matter is made out of? Well, the main way that we know that is through the experiments that led us to these three laws. And these laws we've seen before, at least the law of conservation of mass. We've talked about that previously, about how no matter is created or destroyed when there is a reaction occurring. We have the same amount of stuff at the beginning and reactants as we do as the final products. And we'll also talk about the law of definite proportions and the law of multiple proportions. Now, as you're looking at these, and as we're talking about these, what I want you to mainly be thinking about is, how does this make sense in terms of atoms, in terms of that being the explanation for what we're seeing in the physical world? The law of conservation of mass, we know that one says that whatever I start with, so for instance 7.7 grams of sodium and 11.9 grams of chlorine, that when we get sodium chloride as a product from the mixing of those two things, that what we start with is what we end up with. Now that makes sense if we think about the fact that the sodium is made up of a bunch of atoms and the chlorine is made up of a bunch of atoms. And it's not like those atoms turn into different kind of atoms, like sodium atoms and chlorine atoms don't turn into table salt atoms. What they do is they form a network of connections, and it's those connections that give it the properties of table salt. So what this tells us is we don't have new atoms and we don't lose atoms. We just rearranged how they are bonded. Okay. Now, the law of constant proportion says, and you can read this here along with me, that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. What that means is that it doesn't matter where we get water from. If we get 18 grams of it, we're going to have 16 grams of oxygen, and we're going to have 2 grams of hydrogen. Every time we have 18 grams of water, that's the ratio that we have. And if we had ammonia, for instance, a chemical that had all the properties of ammonia, so we know that's what it is. If we have this, we're always going to find that we have 14 grams of nitrogen and 3 grams of hydrogen. For every 17 gram sample of ammonia we get, no matter where it is in the world, no matter how it is that we made this in the first place, we have these ratios of the two of the elements that make up that compound. That's what it means by constituent elements. So let's look at an example of that. Say we have two examples here, two samples of carbon dioxide, and they're decomposed to their individual elements. One sample makes 25.6 grams of oxygen, and the other makes that same one makes 9.60 grams of carbon. And the second sample of carbon dioxide gives us 21.6 grams of oxygen and 8.10 grams of carbon. Okay, so what does that give us in terms of a ratio, the oxygen to carbon ratio specifically? Well, let's take a look. So 25.6 divided by 9.60, and we get 2 2/3. So 2.67 over 1 as our oxygen to carbon ratio. What about this other example? 21.6 divided by 8.1. We get, the exact same thing. 2.67 to 1 ratio of oxygen to carbon. So this is a demonstration of the law of definite proportions. As long as the sample is carbon dioxide, then we're going to have this constant ratio of oxygen to carbon. Well, this might seem self-obvious with atoms, but this really led to that thought that there must be these individual units of these particular substances if they're always combining in some sort of ratio with each other. And that those units must not all weigh the same thing, because if they did, then it'd all just be 1 to 1 or 2 to 1 or 3 to 2 type ratios, but it's not. Well, so how does this make sense? Well, let's look at this with ammonia. Okay, ammonia, we know now, has the formula NH3, meaning 1 nitrogen, that's these blue spheres, and 3 hydrogens. That's the little white spheres attached to it. If we have 5 molecules in one sample, and 7 molecules in the other, then what we're going to have in one is 5 blue spheres and 15 white spheres. So what's the ratio of spheres there? Well, the ratio of spheres would be 3 to 1. The ratio of masses would be, let's see, we have, this is hydrogen, it's a nitrogen. We can even do that the other way and say there's 1 nitrogen, or 3 hydrogen. Ratios work either direction. Okay. But let's see, 5 blue spheres, each weighing 14, 15 blue spheres, each weighing 1, gives us a ratio of 15 times 1 over 5 times 14. So 70 over 15, which is, drum roll, 70 divided by 15 equals, we have about a 4.67 to 1 ratio of nitrogen to hydrogen in terms of their mass. All right, well, if we have 7 molecules, we know we have 7 of these little blue spheres that are nitrogen atoms and 21 of the white spheres. So if we do the same sort of calculation here, say we have 7 times 14 and 21 white spheres times 1 mass unit each. This is how much the little spheres weigh, that the atoms weigh. 1 mass unit, 14 mass units. 7 times 14 is 98. 21 times 1 is 21. So our ratio is 98 over 21, which, lo and behold, 4.67 to 1. And the reason they have these ratios is all these nitrogens weigh the same, whether they're in a group of 5 or they're in a group of 7. And if I have 5 molecules, then I'm going to have 15 of the white ones. And if I have 7 molecules, then I'll have 21 of these little white atoms. So the ratio of the atoms is always constant, even if I have more molecules, more combinations of those atoms. It's not going to be a different ratio. So 20 or 2 or 10 billion, it's still going to have a ratio of weight of 4.67 units to every 1. Now, the law of multiple proportions is kind of interesting here. That says when 2 elements, let's call them A and B, form 2 different compounds, the masses of the element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. Okay, so we have carbon dioxide and carbon monoxide to kind of look at this idea. We'll call A will be carbon, B will be oxygen. So when these 2 elements form 2 different compounds, and carbon dioxide and carbon monoxide are 2 different compounds, the mass of element B, oxygen, 2.67 grams of oxygen, that combines with 1 gram of element A, right there, 1 gram of carbon, expressed as a ratio of small whole numbers. You're probably saying, well, 2.67 isn't a whole number. Well, that's not what we're talking about. This by itself is just the law of definite proportions, that carbon dioxide will always have a 2.67 to 1 ratio. What we're looking at is the fact that carbon monoxide, since it has a 1.33 grams of oxygen to 1 gram of carbon ratio, that if we look at the ratio of these 2 different ratios to each other, the 2 different compounds, so not 1 compound, but we have to look at 2 different compounds, 2.67 to 1 as a ratio to 1.33 to 1. You divide this all out, it's a 2 to 1 ratio. Okay? So this tells us that whatever is making these things up, there must be more of some part of it, of atom number B in the second compound compared to this compound at the bottom. So this tells us there's more oxygen in this carbon dioxide compound. And sure, we know that now, and we call it carbon dioxide because the di means two, and we call the other one carbon monoxide because the mono means one. So we obviously, these names are given to them after the fact of where we know what atoms are. But this helped us to understand originally that there must be, again, these nice individual units of these elements that are combining in specific ratios. And that's what led to this idea that the units are atoms. We just did this math. See the previous slide. So how does this make sense? Because everything's made up of atoms again. We have a carbon and two oxygens. That's going to give us 2.67 grams of oxygen to 1 gram of carbon. If we have 1 carbon to 1 oxygen, that gives us 1.33 grams for every 1 gram of carbon. There are literally twice as much mass of oxygen in this carbon dioxide because there's twice as many oxygen units. So the whole theory, if we put this all together as Dalton's atomic theory, those three laws combined to come up with this idea that is well proven and well supported by experiments, that each of the elements is made up of tiny, indestructible, which we now know to not be totally true. We can actually blow apart atoms in the right conditions. But the original idea was this: these tiny, indestructible particles, these fundamental units of matter, and those are atoms. We also postulated that all these atoms of whatever given element they are, so carbon or hydrogen or oxygen, must have the same mass, so they're all the same size, or else we wouldn't get these nice even ratios and proportionalities. And they have all of the other properties that they have. They share that with all the other of that type of element. So all hydrogens will effectively act the same. And for the most part, that's true. There are things called isotopes, which we know about now, that have slightly different properties for that element. We also have the part of the theory that says that atoms combine in simple whole number ratios to form compounds. That's just saying we're never going to have like 1.5 oxygens atoms, because atoms don't split neatly in half like that. There's the base unit. You have to add individual whole amounts of them. And that atoms of one element don't change into atoms of another element. Okay? Not at least through regular chemical reactions. So in a chemical reaction, all they actually do is change how they're attached. And so if you sum all this up, it means that you have atoms, which are the smallest fundamental unit of matter, that atoms of a certain kind are the same as all the other atoms of that kind. Compounds are made up of attachments of those atoms to each other. And chemical change just is rearrangement of the attachments, not change of the individual atoms.